Thermodynamics law, first law of thermodynamics, second law of thermodynamics, and third law of thermodynamics. In addition to this, absolute temperature and absolute pressure need to be discussed. First law of thermodynamics. First law of thermodynamics describes about energy conservation in any system. That means heat is equal to work plus energy. So we can write Q is equal to W plus E. Energy in real gas. Enthalpy energy is equal to Cp into T2 minus T1 depends on pressure and temperature, and enthalpy energy is also expressed as it is summation of internal energy plus pressure energy. Again, internal energy is equal to Cv into T2 minus T1 depends on temperature, and pressure energy is equal to P into a specific volume depends on the pressure. Kinetic energy is a half of V2 square minus Vn square, depends on velocity, and elevation energy is equal to G into S2 minus H1 depends on height from reference. Energy in thermodynamics machine. As there is no much difference in elevation at inlet and outlet of any turbomachinery like compressor, turbine, etc., so elevation energy is not considered. In that case, only enthalpy energy and kinetic energy to be considered. If the inlet and outlet velocity is same, then kinetic energy change is also neglected. In that case, only enthalpy energy is considered. First law of thermodynamics used for compressor and expander. In turbomachinery, heat transfer is zero and process is considered isentropic ideally. To have work or power, there should be pressure difference at inlet and outlet of turbomachinery. It is to be noted that value of enthalpy may be different at same pressure at two different temperature, but these change in enthalpy may not be useful to drive the turbine. It is pressure difference which is important to produce power by the turbine. Of course, with the two different pressure and temperature, there will be two different enthalpy. So again, we can write heat is equal to work plus energy, but in turbomachinery, Q is 0. So we can write W is equal to minus E, or in magnitude, W is equal to E. So power consumed by compressor is represented in change of energy of gas. Similarly, power developed by turbine is taken from high pressure gas. First law of thermodynamics used for heat exchanger. In this application, work is zero and process is considered constant pressure. So again, heat is equal to work plus energy, Q is equal to W plus E, but W is 0, so we can write Q is equal to E. Heat transfer represents change in energy level, that means change in enthalpy. As per the first law of thermodynamics, heat transfer is 0 for any turbomachinery as the process is isentropic. And so we can write work is equal to energy. The efficiency of turbomachinery is defined as work upon energy. That means since both are same, it becomes 100%. This is a violation of law of turbomachinery being 100% efficient. How this is possible? Hence, this needs to be corrected to take care of efficiency of machine. So in case of compressor, enthalpy energy into efficiency is equal to work. Similarly, in case of turbine, isentropic enthalpy energy into efficiency is equal to actual enthalpy energy. So to take care of efficiency of the machine, second law of thermodynamics comes in picture. So now what is the second law of thermodynamics? Second law of thermodynamics, the efficiency of any turbo machine cannot be 100% or more. That means efficiency of machine is work upon input energy. So efficiency should be always less than 100%. Second law of thermodynamics for compressor. This is a TS diagram, temperature, entropy diagram. This is a P1, P2, inlet pressure, outlet pressure. So isentropic compression process T1, T2S is a isentropic process where entropy is a constant. In actual process T1, T2, where entropy increases due to friction. So efficiency is equal to isentropic process head rise, that is this process T1, T2S upon enthalpy rise, that is T1, T2, as the enthalpy rise energy is more than isentropic process head rise energy, and so efficiency is less than 100%. Second law of thermodynamics for expander. Again, this is a TS diagram. P1 is inlet pressure, P2 is outlet pressure. So isentropic expansion process T1, T2S is again isentropic process, entropy remain constant, and T1, T2 is actual process where entropy increases. So efficiency will be actual enthalpy drop divided by isentropic enthalpy. Again, isentropic enthalpy drop is more than actual enthalpy drop, and so efficiency of turbine is again less than 100%. Third law of thermodynamics, it is impossible to attain absolute zero temperature by any number of thermodynamic processes. At absolute zero temperature, enthalpy tends to zero and entropy tends to zero. Temperature at which gas becomes liquid. For oxygen, it is minus 183 degrees Celsius. For nitrogen, it is minus 196 degrees Celsius. For helium, it is minus 269. So, to get all these gas, we need to cool down the process up to minus 269 for helium, minus 196 for nitrogen, and for oxygen, it is minus 183 degree. Absolute temperature. Absolute temperature is minus 273.15 degrees Celsius, which is 0 degree Kelvin. Similarly, for absolute pressure, it is minus 1.013 bar gauge or 0 bar absolute. On in Pascal, it is minus 1.013 into 10 to the power 5 Pascal. So, hope you have understood laws of thermodynamics. First law, energy conservation. Second law, related to efficiency of the machine, cannot be 100%. And third law, it is absolute temperature and absolute pressure also we have discussed. So hope you like this. Thank you for watching.